When you say good morning to the bird at your feeder, you think you're sending a voice. But the bird is not hearing what another human would hear. It is not receiving the warmth the same way. It is not processing the words. What it is actually doing is measuring the sound underneath the words, how fast it came, how sharply it rose, how suddenly it changed. And only when you understand that does the number make sense. The pitch of the human voice sits roughly between 85 and 255 hertz. Many songbirds hear most sharply in the range of 1000 to 5000 hertz, with peak sensitivity for many species concentrated around 2000 to 5000 hertz. That is not a small difference. It means the part of your voice you think of as your voice, the fundamental tone that makes you sound like you, is arriving at the bird's auditory system below the range where its hearing is most acute. The bird can hear you, but it is not hearing the part of you that you think matters most. What it is hearing instead is something older, more specific, and in some ways more honest than anything you intended to say. Welcome to Backyard Animals. Subscribe before you leave, because what you're about to learn will permanently change the way you hear yourself talk to the birds in your yard. Today, we are going into the exact science of avian hearing. What birds can detect, what falls below their sharpest sensitivity, and what specific properties of your voice are producing measurable changes in bird behavior every single time you open your mouth. Stay until the end, because the last thing we cover involves a layer of sound that researchers are only beginning to understand. And what it suggests about the conversation happening at your feeder is stranger than most people are prepared for. Let's start with the architecture. Because to understand what a bird hears, you first have to understand what a bird ear actually is. And it is not what you would expect. Your inner ear contains the cochlea, a spiral-shaped structure lined with sensory hair cells that translate sound vibrations into electrical signals your brain interprets as sound. You are born with a fixed number of these cells, somewhere in the range of 15,000 to 16,000. You cannot grow new ones. When they die from age or noise exposure or disease, that loss is permanent. Your hearing degrades and does not come back. A bird's cochlea is shorter than yours and shaped differently. Less spiral, more curved tube. The hair cell count is comparable to yours in many species, but here's the difference that matters. In many bird species, damaged auditory hair cells can regenerate, and hearing function can recover substantially over time. Something mammalian ears, including yours, generally cannot do. This was first documented in the late 1980s by researchers studying European starlings, and it remains one of the most actively studied phenomena in auditory biology, not primarily because of what it tells us about birds, but because of what it might eventually tell us about restoring human hearing. The bird at your feeder is carrying a biological repair capacity in its head that human medicine has spent decades trying to understand well enough to replicate. But regeneration is not what makes bird hearing strange. What makes it strange is the resolution. Birds, especially songbirds, can be extraordinarily precise at resolving rapid acoustic detail. In some experimental tasks involving fast sound patterns, songbirds have outperformed humans in detecting structure within rapid sequences of sound. What this means in practice is that sounds you hear as smooth and continuous, a trill, a warble, a complex song phrase, a bird may be parsing as a sequence of distinct individual events, each one carrying its own information. The song you hear as beautiful but simple may be, to another bird, a dense acoustic transmission, a message packed with detail about the singer's identity, health, territory, and state. You are hearing the broad shape. The bird is reading the structure inside it. This is why bird songs are so compressed. Evolution has packed maximum information into minimum time, because the receiving system can decode it at a resolution humans cannot match. Now, let's talk about frequency in more detail, because this is where your voice enters the picture, and where the gap between what you think you're sending and what the bird actually receives becomes very specific. When scientists talk about the human voice operating in a certain frequency range, they are usually referring to the fundamental frequency, the bass pitch. For a deep male voice, that pitch sits around 85 to 150 hertz. For a higher female voice, around 165 to 255 hertz. But the human voice is not just its fundamental pitch. Speech contains harmonics, formants, and high-frequency components from consonants and sibilants that extend well above that range into the several hundred hertz to several thousand hertz region. These upper components are what make speech intelligible. They are what allow you to distinguish words from each other. Many songbirds hear most sharply between roughly 1000 and 5000 hertz. Some species show peak sensitivity around 2000 to 5000 hertz. That is the range their auditory systems evolved to process with the most precision, because that is where their own vocalizations live. That is the acoustic bandwidth of birdsong. Now look at where those ranges interact. The upper components of human speech, The formants and consonant frequencies that carry word meaning do reach into the lower edge of where many birds hear most sharply. So the bird is not operating in a completely separate acoustic world from yours. There is overlap. But the overlap is not where you probably imagine it. The fundamental tone of your voice, the quality that makes your voice sound warm or soft or gentle, the part you are consciously projecting when you speak kindly to a bird, that sits below or at the edge of where the bird's hearing is most precise. The parts of your speech the bird processes most clearly are the higher frequency components, the sharper sounds, the consonants, the sudden changes, not the warmth, not the tone, the structure. It does not mean the bird cannot hear you. It means the parts of your voice that matter most to you are not necessarily the parts that matter most to the bird. Experiments with birds have shown that they can learn to discriminate between complex sounds, including human-made acoustic patterns. Individual birds, particularly those with extended human contact, can learn to respond differently to different people's voices. But what they are most likely using is not word meaning. It is pitch contour, rhythm, repetition, loudness, and consistency. They are reading the acoustic behavior of the sound, not the content. This is where the real conversation happening at your feeder becomes clear. Because if the bird is not processing your words and is not receiving your fundamental tone with peak precision, what is it actually measuring? The answer is three things, and all three of them are operating below the level of what you think of as communication. The first is tempo, rate of speech, speed of vocalization. Across many bird alarm systems, rapid, sharp, abrupt sounds often carry urgency. Alarm calls are short, quick, sudden. Aggressive territorial song is delivered at high rate. When you speak quickly, in short clipped phrases, the tempo of your voice pattern matches the acoustic signature of elevated activity, regardless of what you are actually saying. The bird's auditory system is not processing your words. It is measuring your rate. Slow, continuous, low variation sound is often closer to background than to alarm. Wind, water, leaves moving. These are ambient sounds, the sounds of an environment where nothing threatening is happening. When you speak slowly to a bird, when your rhythm becomes smooth and unhurried, your voice moves into a different acoustic category in the bird's threat assessment system. Not the threat category, the background category. And being categorized as background, as part of the ambient safe environment, is the best acoustic outcome you can achieve. The second property is amplitude variation, how much your volume changes within a sound. Sudden amplitude spikes are the acoustic signature of events that matter. A branch snapping, something landing nearby, a predator arriving. These are characterized by abrupt changes in loudness. A voice that stays at consistent, low volume with minimal sudden peaks reads as acoustically stable. A voice that rises and falls sharply, even in the course of a single enthusiastic sentence, produces a series of small acoustic events that a bird's system registers as changes requiring attention. This is why animal handlers often arrive at the same conclusion through experience. Sudden volume changes startle birds far more reliably than a steady, quiet voice, even when the quiet voice is saying nothing meaningful, and the loud voice is saying something kind. The bird is not evaluating the kindness, it is evaluating the amplitude signature. The third property is the most unexpected, and this part requires some care, because the science here is real, but the story is incomplete. Some birds, particularly homing pigeons, have been studied for their sensitivity to infrasound, sound below the threshold of human hearing, below 20 hertz. Researchers have explored whether pigeons use low-frequency acoustic cues, including infrasound produced by geographic features like mountains, coastlines, and atmospheric circulation, as part of their navigation system. The evidence that some birds can detect infrasound is documented. The research on how they use it for navigation is ongoing. What is less established, and what requires honest caution, is how far this extends to backyard songbirds in the context of human proximity. The human body produces low-frequency vibrations as byproducts of breathing, chest resonance, and vocalization. Whether a cardinal at your feeder is detecting and processing those signals in any meaningful way is not something the current research can confirm. It is possible. It is an open question. It is not a proven fact. What the infrasound research does tell us is simpler and stranger than the specific claim. The acoustic world birds inhabit may contain layers of information that humans do not perceive and have only recently begun to study. When you stand at your feeder and speak to a bird, you are producing sound across a range of frequencies, some of which you can hear, some of which you cannot, and some of which science is still in the early stages of understanding. The conversation may have dimensions you are unaware of. That much is real. The exact nature of those dimensions, for this species, in this context, is still being worked out. Here is what you should take from all of this. When you speak to the bird at your feeder, You're not sending the signal you think you're sending, the fundamental pitch that makes your voice sound like you arrives at the bird's auditory system below the range of its sharpest hearing. The warmth you project is real to you, but the bird is not decoding it the way another human would. What the bird is measuring is your pattern, your tempo, your amplitude consistency, the acoustic behavior underneath your words, the properties of your voice you never think about. The ones that operate below the level of intentional communication are the ones doing the most work. This is why the advice to speak slowly and quietly to birds is not just intuition or folklore. It is acoustics, a slow, low amplitude. Consistent voice is not simply calmer. It is, in the bird's auditory world, a measurably different category of sound. It reads as background. It reads as safe. And safety is the only acoustic currency that matters. The cardinal at your feeder this morning heard you. Not your words, not the warmth you felt when you said good morning. He heard your tempo and your amplitude pattern and the acoustic signature you produced without knowing you were producing it. He ran all of it through a threat assessment system calibrated over millions of years of evolution. And he made a decision about you in fractions of a second, based entirely on acoustic data you did not know you were transmitting. That decision, made from frequencies and patterns you never intended to send, is the real conversation happening at your feeder every morning. You just did not know it was the conversation. Now you do. Tell me in the comments, have you ever noticed a bird respond differently depending on how you were speaking? Did it stay longer when your voice was quiet and slow? Did it flush the moment your volume rose, even slightly? I want to hear about it. I read everyone. I'll see you in the next one.